Paul, you're muted.
I think I'd figured that out by now. Thank you. So what I was saying is all the stuff that is in the final exam review, except for like what the focus on, is just stuff that I copied from the previous exams because, as I mentioned, I'm a realist and it's hard to expect people to learn new material or study different material. And so we put a lot of detail in the descriptions for what to study on. So it's basically a summary. It's also 11 pages, but hopefully you get the whole kit and caboodle. We started off by what's the difference between average power and instantaneous power? Because in DC circuit analysis or any time domain circuit analysis, there's no such thing as an average power. But what is important to us when we do AC or steady state analysis, we must make sure that we're looking at a power over one sine wave. We're doing with voltage, we're doing that with current, so we have to do the same thing for power. And if we think about it, we have an average power as long as the voltage and the current, when they're multiplied together, gives us a value that's above, the zero of the zero crossing. With voltage and current, we can't use average voltages and current because over one sine wave, the average voltage and current would be zero. So we use the concept of an RMS, which is a way of taking that negative value and flipping it around. And then that whole square root of 2 stuff that we developed is all based on making our power equations work correctly. If we're looking at purely resistive load, we want P to be equal to V times I. Well, if we did V of T and I of T and we multiplied it out, we'd have to divide the magnitudes of the voltage and current by 2. So what we do is we distribute the 2 into 2 square root of 2s, and then we divide each one individually, and that's where we come up with the RMS quantities. Okay? It just so happens that RMS is a term we use because that's how the math works. So what is in your outlet is 120 volt RMS, not average, but RMS. If you did the time domain, what's in your outlet is 167 sine of 377 T, right? That's the actual time domain representation of that. So that was pretty important to us. And once we understood how we got this average power, we realized that sometimes the average power is not being conveyed completely to the load. Sometimes the power that is stored in magnetic fields or electric fields has got to be sent back to the source, the generating source. So what we determined at that point is we have to develop another term to characterize that borrowed power, that power that's got to get sent back. And we came up with the term Q for reactive power. So our total power was P, the real part, in watts, plus J times Q, the reactive power in bars, and that was equal to S, the apparent or total power of our system. So when we add those two together, we have to include the J term because what we're doing is we're saying that power is imaginary. It's really not imaginary, right? It's just a mathematical representation to say it's not doing any useful work to the load. So that's why it's power that goes and come back. But it's real power. It's real energy that's being delivered to the system, but it's got to be sent back. That's essentially the Q. And then that also introduces the concept of Eli the ice and a leading and lagging power factor. I've harped on this enough times. You're probably sick of me saying this, but Eli means that the current, not the voltage, but the current lags the voltage in an inductor. And in a capacitor, the ice part, the current leads the voltage. Okay? So leading and lagging is always relative to current. And whenever you specify a power factor, which is just the ratio of P to S, you need to define if it's lagging or leading. Giving me a negative power factor doesn't give me an answer. I need to know, does the current phasor lead or lag the voltage phasor? Once you provide that information, then you know all the details. And if you're confused on an exam about leading or lagging, and if I'm giving to you, it's 100 megawatt of load at a lagging power factor, remember that lagging power factor always refers to what the current is doing to the voltage. So draw your phasor diagram and then do the S equals VI conjugate equation to see how you can build your power triangle. Okay. So we looked at phasor diagrams too. Phasor diagrams are a really convenient way to kind of look and see how the system is operating. And it helps give us an idea of what's happening in terms of voltage drops as well as phase shift. So looking at voltage drops tells us typically how much reactance is in the system. And phase shifts usually tell us how much load or how much real power is moving from one point to another. And then looking at those phasor diagrams just gives you a really good sense or a good image of what exactly is happening in my system. So my hope for all of you up to this point is, including section 3, that this was all reviewed. That was my hope. I'm not saying that's exactly what happened, but that was hopefully what happened. Because you've also should have been exposed to impedance. And impedance is just a way to convert a capacitor and an inductor into a steady state analysis tool. Otherwise, in the time domain, we have to take derivatives or integrals to calculate voltages and currents for circuits with inductors and capacitors. But in steady state, the whole purpose of doing things in steady state is to not do derivatives and integrals. The really big joke is everybody here probably started out taking math and has taken 3, 4, 5, whatever semesters of math. You know, a lot of calculus. Well, in reality, what real world engineers do is do as little calculus as possible, because the math is not necessary to get answers. So the likelihood of you doing a derivative or integral when you get out in the real world is pretty low. Not saying it's zero, but it's pretty low. And so that's why we do Laplace. And in this class, that's why we do AC circuit analysis. So that's why we introduce the concept of X sub L and X sub C. The J term is there again to introduce the phase shift that inductors and capacitors provide. With a resistor, there's no difference. Okay. And then this was a good time to talk about what Q was. So V squared over R, or V squared divided by I squared, V squared over R or I squared times R was the power, real power. We could do the same thing for Q, just substitute X for R. But the highlight of this was, keep in mind that we have to use the magnitude of the current or the voltage. And the reason why you have to use magnitude is because, well, first off, because when we do the conjugate, S equals VI conjugate, the angles will change and cancel out any angle that's associated with those voltages or currents. But secondly, when I do Q, I should only have a scalar number. Remember, P and Q themselves are scalar numbers. It's only when you combine them into S to get the total power is when you include the J term. So magnetics, that's the key for us in this class to move from typically, not always, but typically to move from the mechanical world to the electrical world and back. So we had to do a little bit of discussion about how that magnetics actually are introduced. We're not pretending to be experts in it. If you want to become an expert in electromagnetics, ECE has 351, ECE 351, which you're welcome to take. There's also some engineering physics courses when they do electromagnetics. It's not necessary to delve into it in that level of detail for us to be able to take advantage of them, because we can make some assumptions and simplify our math. We also use magnetics for transformers, and transformers have electrical isolation between the primary and the secondary, unless they're connected. I actually reviewed a circuit for somebody over at the structures lab that they had a 480 to 208 volt transformer, and the 480 was delta connected and the 208 side was Y connected. And he showed the neutral all connected to the same point, but he didn't show a ground. And so he was even confused about, well, ground is ground is ground. Doesn't that mean that all my electrons will be, or my current will flow back to ground? I said, no, because you've isolated the ground on the secondary side of the transformer. And that's because the magnetic energy, right, the transfer of energy magnetically means that that 208 volt source is completely isolated from ground unless you reference it to ground. Okay, so magnetic circuits do that really well for us. We did three-phase circuits, which are hugely important to us because most of the industrial world, even the commercial world, and maybe even residential in the future, who knows, right? As we get EVs, as we plug in more and more EVs, we like to have 50 amp plugins. But does anybody know what a supercharger charges at? Some of them like 200 kilowatts, really high power levels. And you can't get there with a single phase circuit. So maybe if everything becomes electrified, we might actually have to run three-phase circuits to all individual homes because we need to power up our cars. Maybe we won't, I don't know, because with a Tesla, I think you can get 100 kilowatt battery can get you 300 something miles. So, you know, if you can charge it for 10 minutes at 50 amps, maybe you get 20 miles or 30 miles to go grocery shopping, but then maybe you have to pay for the superchargers wherever. So that's the importance of using three-phase circuits. Three-phase circuits, we did delta Y connected circuit. We have phase voltages that are different from line voltages, but phase currents and line currents are the same. We also saw that there was some phase shift between the voltages, not because of the currents, because the currents are the same, so you can have phase shift. But with voltages, you did have a phase shift, and it depended on if it was ABC or ACB. In a delta, the voltages were the same, line and phase were the same, but the phase currents were not the same as line currents. And that means we also have that plus or minus 30-degree phase shift. But what we know is that we always have the square root of 3 if they are not the same. All right. So this is when we started introducing the square root of 3. This is the only equation. These two equations here are the only time we use square root of 3, right? And it's base equation. Because when we look at impedances, when we go delta Y, we multiply by 3. When we talk about power, we multiply by 3 for the individual phase. But square root of 3 is only for the voltage and current. This is the only time we did that. And that's just because of the geometry. When you add those vectorially, you get the square root of 3 term. Everything else adds as a single phase quantity. So you don't have to deal with that. Now, I did say we only use 3 in all of our equations. But over here, I've got the square root of 3. Well, I'm just being cute. So the absolute correct equation is for a 3-phase load. You have the total 3-phase load is just the sum of the individual phase loads. So it's S1 plus S2 plus S3. But in this class, we're dealing with a balanced system. So S1 is equal to S2 is equal to S3. So I can just say it's equal to 3 times S1 or S2 or S3. But those are individual phase quantities, right? I'm talking about single phase representations. Over here, I've gotten sneaky, and now I have V and I. Those are line quantities. So I haven't changed the equation. I've just substituted in some variables. I don't have V phase or I phase over here. I've got a square root of 3 that's introduced. So the way that I take that into account is I have to divide one of those extra square root of 3s out of there, and then I can use this equation. So this is the time that the only other time you'll see square root of 3. But again, that's because I've substituted in different voltages to hopefully make the calculations a little bit easier. We add powers vectorially. Sorry for the typo here. I just copied it over. I should have fixed it because it's not vectorially, whatever that is. But power just adds because they're complex numbers. You have to add them as complex numbers. You can't add them as scalar numbers. VI and impedance and transformers. So transformers really make the world go because they can significantly reduce line losses, which allows us to put generation long distances away. Like if we were campus here and we're 10 megawatt of load, if we can allow really long distances for carrying power or moving power, all the generation for campus would have to be on campus. And there is some generation on campus. I think there's 600 kilowatt back pressure turbine at the steam plant, but that's 600 kilowatts. We need 8,000 kilowatts. So we're not even close to getting there. So what you can do is you can rely on the grid to provide the load that you need. So we can have some power taken from VZ, which is 7 miles away. We could also maybe get some hydroelectrics that's around. And so what happens is by running the system at higher voltage, you can get bigger generators and you can locate them strategically. You don't have to have them next door. You can locate main independent station on a river. Why do you locate it on a river? Because I need a lot of makeup water. If you ever notice, most power plants, and this is traditional power plants, tend to be located near fairly large bodies of water. I even went to a large coal-fired facility in Arizona, and it was near Flagstaff, Arizona. Not a lot of water up there, right? Pretty dry. They have aquifers. They have huge aquifers where they have billions and billions of gallons. So they got all their water from underground, but they need that for cooling. And so transformers allow all this to happen. So you don't have to have generation located near population centers. And it used to be a lot more important because all the generators that we had were steam, they were steam for the most part, which means they were burning coal or some other things. And you wouldn't want, excuse me, coal stacks and all that stuff in Midtown Manhattan, right? People on the 30th floor are going to get all the fragrances from those plants wafting into their apartments. So you locate them further and further away. But that transformer allows us to generate at a reasonable voltage, 13,000 volts, 14,000 volts, maybe even 25,000 volts. And we can make our generators much bigger, which means we can get economies of scale. And then we can ship that power out to all the different load. Well, if I have a nuclear facility that's putting out 2,500 megawatts, I need a lot of load. And most likely that load's not going to be nearby. So I'm going to set that voltage up to a much higher level so I can reduce the line losses. So transformers originally were all about reducing losses in the system. The very first transmission, quote unquote, system was getting power from Niagara Falls to Buffalo, New York, 20 miles away, not all that far, but it provided some big advantages to be able to reduce line losses. And you had all that hydroelectric resource available to you. It was essentially free energy ready for the taking. You just had to convert the energy from the mechanical part to the electrical part. So the transformer takes the voltage and steps it up or down, and the opposite happens with the current. So if you set the voltage up, you step the current down. If you step the voltage down, you step the current up, which is a good thing because we want these transformers to deliver a constant amount of power. Our transformers, yes, we can use them for electrical isolation or impedance matching, but the vast majority of transformers are there to convey power from a higher voltage to a lower voltage. In generator sub-up transformers, it's the opposite case, but in most cases where people are interested in, it's to take power from a higher voltage and step it down to a lower voltage. And we want all the power going to the transformer to be delivered to the load, because if it's not, power is being wasted. We don't want to have an inefficient system. We're competing with our friends in mechanical engineering to make sure that we deliver the biggest bang for the buck. So we've got to do that at very high levels of efficiency, which fortunately we do. And then the only other thing is because you step voltages up and down, when you look at impedances on one side of the transformer, you can reflect that impedance through that transformer. And as long as it's equivalent, the current that goes into that transformer has to be the same, whether I have that transformer and the load or an equivalent load resistance on the high side has to look the same. And so you just have to use the turns ratio. Here's our equivalent circuit model. We're probably pretty comfortable with this because we've been looking at induction motors, but it's basically 6 elements. You have resistors, 3 resistors, and 3 inductors. 2 of the resistors are as a result of core or coil losses, I should say. One's because of the core. You've got 3 inductors. 2 of them are because of leakage as a result of current flowing into the windings. And the other one is you have to magnetize the core. And as we talked about, every one of these devices you've already been exposed to in your introductory circuits, except for perhaps the transformer. So this is a new electrical device that we have to develop that we haven't ever seen. And so this is the only device that you may not have seen that you have to add to analyze almost any other circuit. Talked about power supplies. You've already been exposed to that. Resistors, inductors, capacitor. You've already been exposed to that. You got to add that 5th one, which is transformers. And for any linear system, that's pretty much all you need to model it. We also did some open and short circuit tests. So if we built a transformer, we need to make sure that the transformer, we know what the results are. So we can run an open circuit test, or the other term we talked about is no load. And we could do the short circuit or the load loss test to calculate all the parameters that we need to. And this no load and load loss test, or open circuit and short circuit tests, are actually applicable to different systems, synchronous generators and induction machines. And we'll see that a bit. Now we moved into AC machines, and we spent a lot of time where we developed magnetic fields in AC machines. Where we took our hand and we pointed in the direction of current going into a coil of winding, a coil of wire, and then we wrapped it around in the direction, and then our thumb basically pointed in a plane that was perpendicular. So that's the thing about magnetic fields. They often are going in a direction that is orthogonal to where the current is flowing. So that's why if you look at my hand, maybe it's not the perfect perpendicular, but if I'm wrapping this way, I can pretty easily see that this is my perpendicular plane or orthogonal plane. So that's when we did the approach where we had currents going into coils, and then we had magnetic fields. Magnetic fields add up all together. So you would add the individual magnetic fields, right? Because they're just magnets, they're north and south. It's not like you have electrons where you have to have a reference. These just will repel or attract as necessary. So you added them up to get a net magnetic field. And what we saw is when we ran through our sine wave as we quote unquote rotated through our sine wave, which is just another way to say time has elapsed, we saw that our magnetic field rotated. And if it was a three-phase machine, we saw that magnetic field rotated, but its magnitude never changed. It was always at 1.5 times the magnitude of any maximum individual phase. So it was constant, which is what we want because that gives us a chance of constant torque. And so all we did for the initial part about AC machines is we ran three-phase currents into the stator winding and we got a rotating magnetic field, which is a good thing because if we're using an AC machine, that's another way of saying we're rotating something or something is being rotated for us, which we need to have that rotating magnetic field to be able to do something useful. And then that started to introduce the concept of synchronous speed. The whole thing about synchronous speed is the magnetic field is rotating at that speed and it's not changing. And the synchronous speed is determined by two things, the electrical frequency and the number of poles in the machine. So you can take any AC machine in the United States and bring it over to Europe and it'll work fine. It just won't work at the speed that is indicated on the nameplate. It'll operate at a slower speed because they operate at 50 hertz. And then how do you get the relationship? You can adjust the speed, the synchronous speed, by increasing the number of poles. So the more poles you have means the slower the synchronous speed, the rotational speed of that rotating field, which means the mechanical speed is also going to be slower. Doesn't need to go as fast to keep up with it. And then we look at losses in a machine. Because it's a machine, we have a motor or a generator. Power can flow in either direction in AC machines. So on the top case, we know it's a mechanical power out because it's indicated as a load. Or you can also look at it and see that the input power is electrical power. So electrical power in, mechanical power out means that's for a motor. And then we start dropping loads. We have some I squared R, some core losses, and then everything at this point is developed power, right? It's power that's mechanical. We didn't include that here because for the most part with synchronous machines, they're synchronous generators. So it didn't make a lot of sense to include the developed part. We were just looking at it electrical. Now we take out mechanical losses and then we're ready to apply torque to a shaft of some mechanical system. The opposite case, our mechanical power is input. So we have some sort of torque being supplied by something. I don't know what it is, but something. Now you got to take out the opposite. You should need to take out the mechanical losses first, then you take out the electrical losses, and then you've got an output actual power. And then this power here is induced. That's why you can see there's a torque that's here, because if you didn't get any electrical power out, that would give you an induced torque. The unit would continue to spin up. It would speed up and speed up and speed up until it got damaged. But the electrical power out is giving us an equivalent or an induced torque. So then we moved into synchronous generators. And we focused mainly on synchronous generators because that's where most of the power in the world comes from. And you can say, well, solar is becoming bigger and wind is becoming bigger. Yeah, I agree, but it still pales in comparison to the amount of synchronous generation that's around. If you looked at just the nuclear power that's in New England territory, that's almost 4,000 megawatts. That's probably all, just those three units is more power that's being produced from synchronous machines than from any PV or wind. Now, PV or wind is catching up, but there are some problems with that because when we have synchronous generators, we have hunks of iron. We have mechanical systems that are driving that. And so when faults occur, the energy is extracted out of those over time. You can't get a solid piece of mass with all this inertia to stop instantaneously unless you're pulling out a lot of power. But in PV system, there is no inertia. It's just light being converted into electrical energy. So it's very easy to take the power off. How do you do? Just throw a blanket over your solar cell. That takes all the energy away, right? So there's no inertia. I mean, electrons, if they're moving, have some inertia, but what is the weight of an electron? It's negligible. So that is causing more problems. So that's why we still need to spend a lot of time talking about synchronous generators. And in anything in electrical circuits, we always understand a little bit about the operation, but we want to analyze synchronous machines, which means we have to come up with an equivalent circuit. And a synchronous machine on the AC side of things has a power source, some inductors, and a resistor. And that's it. Very basic, very simple equivalent circuit. As long as I'm not including the rotor circuit. Remember, the rotor circuit is oftentimes going to be provided with a DC current or DC voltage. And that's going to allow us to either increase or decrease the excitation to make the system more lagging or leading. I don't show that here. Why? Because what we learned from the second test is it doesn't affect our calculations. We can't include any of the DC stuff in our calculations because our calculations are done on the AC system. And then we did the same thing. We did open and short circuit tests so we could come up with some curves because we can't access this voltage because it's behind these two internal impedances that are equivalent. So we did open and short circuit tests to allow us to, at certain field currents, we can compare the stator current and the terminal voltage to be able to calculate impedances. And that's when we had those curves, and we looked at a pair of curves from the pump storage facility in Western Mass. Short circuit ratio, we don't really use it all that much, but it's just the ratio of field current at rated voltage to field current at rated current. Not particularly useful, but you see it every once in a while. And a synchronous motor is the same thing. It's a synchronous machine, but now we actually have our shaft power. The power that is going into the system is mechanical. And I debated covering synchronous motors because you hardly ever see them, at least back in the day. Now they're becoming more common because, again, because of renewable energy sources and the low inertia, they actually make running the grid very difficult. So how are we fixing some of the renewable energy problems? We're using old technology, right? We're going back to using good old synchronous generators or synchronous machines that have inertia. So how do you make a system with no inertia? You add a system with inertia, and then hopefully they balance out. And then we moved on to induction machines. So induction machines were really, really important for us because that's where all the mechanical power, almost all the mechanical power is distributed. And we saw how mechanical systems that use induction motors cannot operate at synchronous speed. And we always have to have a speed difference. And it's so important to us to focus on that speed difference that we developed the concept of slip, which is the actual speed difference between what the mechanical system is operating at versus the synchronous speed. So we developed an equation for slip, and we saw that slip varied from 0 to 1 if it's an induction motor. At a slip of 0, it's at synchronous speed, which it can't operate at unless it's being pushed. If it's a slip of 1, then you're under locked or blocked order conditions and it's not spinning at all. Those are the two extremes that you have. And that allowed us to expand our understanding of, okay, well, how does this induction machine work? Because we know to get something to rotate, we need, or something to move in general, we need a magnetic field that has a north and a south and either repelling or attracting another north-south. So we already talked about how we generate a stator magnetic field because of the currents that flow in the machine. It's the same thing over here. We have that same stator part, but the rotor is different. And the rotor will get its current or magnetic field from current flow that is induced from the stator circuit. The only way you can get a current flow is you've got this changing magnetic field seen by those coils of wire in the rotor circuit. So it cannot operate at synchronous speed. It has to operate at difference. And that that current that's on the rotor circuit is an AC current, whose electrical frequency is determined by the slip. And that's the difference in speed because the rotor field is going to operate at the same speed as the stator field, which is a good thing because, again, we want constant torque. If they operated at different speeds, then we wouldn't have constant torque, which means you'd have to come up with a new design or new configuration. Then we developed torque versus speed characteristics. And so we saw, or we developed in class, we saw some pictures or images of torque versus speed characteristics. Later on, once we saw equivalent circuits, we actually built our own torque versus speed characteristics. But essentially what it does is it shows you how slip is varied from 1 to 0, or from speed goes to 0 RPM all the way to synchronous speed. And our torque versus speed characteristic for a NEMA design B was we had pretty good starting torque, 200 to 300% of the full load torque. And then that value tended to increase until you got to what our pullout or our breakdown torque is, which is the maximum torque this particular machine can produce. And then we wanted to get down to the full load output torque, which is very close to operating at synchronous speed. And the reason why we figured that out is because when we looked at the equivalent circuit, we were wasting energy at lower values of slip. So running a machine at 1 or 2% slip means it's a higher efficiency. So we don't want to run a machine at 1,000 RPM. We want to run it at 1792 RPM, as close to that as possible. We could change the NEMA design characteristics. So we had B, but we could have gone all to D, which means all of the starting torque, all of the breakdown torque is available for starting, which is great, but there's a big problem with that, and it's efficiency. Because we're not running, because our curve is not as steep on the way down, our full load torque occurs at a slower speed than a NEMA design B, which means we have a less efficient machine. And then here's our motor equivalent circuit, which again is essentially the transformer, but everything reflected to one side with a short-circuited output. This is the whole kit and caboodle. We did combine R2 over S. So we combine the rotor resistance plus the output torque, the developed power. We included in one because it simplifies the calculation, but you're welcome to treat those as two separate resistors if you want. And that's what I did over here. When I did the loop equations and I set it up in a matrix, you can see that nobody ever commented I have a typo here. That's R2 over S, not R1. So sorry about that. Guess I just copied the R1 over. But you can see I combined them over here, but you certainly could put R2 and then R2 times 1 minus S over here. It just means your equations get to be a little bit long. Now, you're welcome to use loop equations, or you're welcome to use a Thevenin equivalence to calculate stator and rotor currents, or you can just do your own calculations, whatever you want to do. It's just that entering this in a matrix takes a little bit of time, right? Whereas doing the Thevenin equivalence is not so much time. It doesn't take so much work. And then here's our power flow in an induction machine. It's only going to be an induction motor. We're not going to really look at induction generators. They do exist. They're more common now, but they're always using a wound rotor design, and it makes that design more complicated to analyze because you've got some external rotor circuits that are happening. And actually, a doubly fed induction generator, they actually build in a specific frequency and put that on the rotor circuit. So they don't even rely. It's kind of considered an induction machine, but in some ways it's not, because you're actually injecting a current, a AC source onto the side, but it uses the principle of an induction generator, but it's truly not getting its field induced. So our input power is electrical, and then we start dropping off electrical power losses that are on the stator. We jump through the air gap. Now we've got our rotor losses, and at this point, all our power available is mechanical power. And then we actually have power to drive a load. Here are some equations which actually show us that concept about efficiency, which shows the lower the value of slip, the more rotor copper losses I'm going to get as a function of the input. And then you can use the Thevenin theorem. Again, if you want to use MATLAB, you don't need to use the Thevenin theorem. You can just do what I showed you how to do, which is just do hundreds of calculations, and you can get all this information. If you prefer, you can just write these equations down and go from there. And then lastly, I think this is last, maybe there's one more. I wrote this a couple days ago. So if we actually need to get parameters, we can do locked and blocked rotor tests, because it's wonderful to have an induction machine. But if we want to come up with an equivalent model, what we're going to have to do is run it through its paces. So we're going to have to do those no load and load loss tests, and we can do the calculations here. So remember, no load tests or the open circuit test doesn't exist in this case. So what we're doing is we're running it under with no load. The shaft is just spinning along. Under the load loss test, we have to do what's called the block rotor test. So we're locking in the position, and we're able to calculate most of the parameters by using those two tests. But we still need one additional equation, which here is our final set of equations. Depending on the type of NEMA design it is, you can relate your X1 and X2 as a function of your locked rotor conditions and get that. So keep in mind, we do the DC test to get R1, the open circuit or no load test, we can get the value for R2, and we can get the value for X1 plus XM. And then a load loss test, we're going to get X1 plus X2, those values. And then we just need to pull out and get the XM value. And then last thing, if you want to start a motor, use a VFD. That's what everybody uses today. If you're cheap, use an auto transformer. And what we saw in lab is you could put out less speed and less torque when you ran it at a lower voltage. And you can actually see that when you look at this equation back here. You can see for T induced, it's directly proportional to the Thevenin equivalent voltage. So how do you reduce the Thevenin equivalent voltage? Just apply it at a lower voltage. That's what an auto transformer. Here's what to focus on. The final is going to be comparable to the last couple tests, maybe a little more difficulty because you get 2 hours. And in an exam, we've only had an hour and 15 minutes. So you have an additional 45 minutes. Where is the exam going to be? In this room from 8 to 10, a week from today. Please don't complain about the room or the time or the date. I have nothing to do with that. The only thing I have to do with it is I just say, yes, I'm having a final. Somebody else determines the schedule. So I literally have nothing to do with it. If you're unhappy with it, go complain to student records because they came up with a schedule. I'm at the mercy of it as well. So I just do whatever they tell me to do. Questions? Since I've been blabbering for almost 40 minutes. Nope, you get 4 sheets, right? You get the one for each exam, and then if you want to add in additional information, you can get that 4th. And as I encouraged you, when everybody turned in their tests, when they took the exams, they asked me if I wanted their sheet, and I said, no, you can keep it. I didn't say, no, you can pitch it. I said, no, you can keep it, right? So maybe that was too subtle, but if you kept that sheet, then you can actually use that because you spent a lot of time putting that together or those together. Why not reuse them for the final? If you're going to do the exam remote, it's the same deal. I'll have it set up because we do have some people taking the class online. All I need is you to let me know and just have a camera available from 8 to 10.
Do they have to be the same sheets as the exams, or can you make new ones?
You can do new ones. If you sit there and write 4 new sheets, though, I am impressed because you got through a whole new semester. A lot of work, but you're welcome to do that. Questions? DPC 115, yeah, that's what it said, right? Any other questions? All right, well, thank you for attending this class. I know there are a lot of people. We did a lot of stuff, so hopefully you learned a lot. And I think you should all congratulate yourselves compared to where you started, where you are today, and look at what you've learned. If I had put at the beginning of the semester, and I said this in my earlier class, this information, can you give me these problems? You would have turned around and walked right out the door, right? Saying, I don't even know what you're talking about. But now you can look at these and say, wow, I can actually see how I can solve some of these things. These make sense, which is hopefully preparing you for a career in industry. Because this is the type of equipment you're going to come across. You're not going to come across breadboard circuits. Most of you, I would say 99.9% of you will not have breadboards with RL resistors, inductors, and capacitors in them. We just don't do that. Everything now is surface mount. It's all designed on a computer. So you don't see a lot of that stuff. It's all done with robotics. But all these motors and stuff or loads, you might not see them individually, but aggregated, you would certainly see them. So just think about how far you've come and give yourself a pat on the back because you've accomplished a lot. And for those of you who are done and graduating, make sure you focus that you did a big thing. That's really an accomplishment to get a degree. It's a lot of financial commitment, a lot of time commitment. What I told my class earlier today is if you have any inkling, go to graduation. It's one of the few times in your life where everybody's happy for you. Literally, it's one of the few. I gave the example about marriage. There's always somebody who's going to be mad that you're marrying that person. Nobody at your graduation or even in your life is going to be mad that you graduated. Even the people that said, why are you going to college, you fool? You're going to waste all that time and money. They're going to look at you and say, wow, you went to school and you finished. Congratulations. They're going to be happy that you finished. They may not agree with your decision to go to college, but they'll be happy that you're done and you got this degree. So savor that time. It really is one of the few moments in your life where everybody's happy for you. That's why graduation is such a special day. It's really a big deal. So, take time because life is fast and quick. And if you don't recognize some of these major achievements or milestones in your life will just blow right by you. And so graduation is an easy one. It's not like you have to take a job in Michigan and travel away and, make all new friends and all that stuff. You just have to go to graduation. You already know the campus. Just gotta invite your family. Make sure you get here early though, because traffic can get a little crazy. I usually get here around 8 on graduation morning, and ours doesn't even happen until 2. We have some stuff that happens with Francis Crow and all that stuff, but yeah, I usually get here at least 2 hours before the craziness starts. Any other questions or comments? All right, I bid you adieu and have a great rest of your week. And I will see you all. If I don't see you early, I'll see you on Thursday. Take care, everyone.
See you, Paul.
Thank you.